Hello friends, IBM is here with an episode of Learning Physics with me, and today I would like to take you through medical physics. I think this will be two episodes, if God willing. I think it will be two episodes. So medical physics, we are actually looking at physics 9702, that is paper 4. And medical physics is most likely going to be one of the last questions in paper 4, as you'll be seeing. So in medical physics, we are going to discuss parts such as ultrasound scan. We are going to see the X-ray scan. We are going to see the CT scan and the PET scan. So the solved past paper questions will actually rotate around ultrasound, X-rays, and CT scan and the PET scan. So the first two questions will concentrate on ultrasound and maybe a mix-up of CT and X-ray scan, but as we advance towards the end of the unit or towards the lesson or maybe in episode 2, we shall actually see some questions about PET scan. Remember, PET scan is still new, so the questions are still very few, but we shall use those which are available and try to get a glimpse into what a PET scan is. So let's straight away move to the document. Let's straight away move to our document of medical physics, of our past paper questions. You must have this document in hard copy. If you want to make learning interesting, you try to work out. We always learn easily by doing rather than just watching and listening. So these are the sample questions you will find in or about medical physics, and let us start. Number 1. By reference to ultrasound waves, state what is meant by specific acoustic impedance. If you have studied some medical physics, you notice that we normally use Z for acoustic impedance. So when somebody talks about acoustic impedance, the letter Z comes into mind. And if you remember, your teacher must have told you that Z stands for density Z stands for the product of density times the speed in that medium. So we define acoustic impedance Z as the product of the density of the medium and the speed of ultrasound, the speed of the ultrasound or the ultrasound wave in the medium. The density of the medium, product of the density of the medium and the speed of the ultrasound wave in that medium. That's what we called the acoustic or specific acoustic impedance. So a parallel beam of ultrasound of intensity I is incident normally on a mass of thickness 3.4 centimeters as shown there. The ultrasound wave is reflected at mass-bone boundary. The intensity of ultrasound received back at the transducer is IR. Some data for bone and mass were given, so they have given us the specific acoustic impedance. These are the Z values. Z for bone is that, Z for muscle is that. The linear absorption coefficients, that is mu, these are the values. And then the first part of the question, they're telling us that the intensity reflection coefficient, remember that is the ratio of the reflected intensity to the incident intensity at the boundary. Intensity reflected at the boundary over intensity incident at the boundary is what we call the intensity reflection coefficient. So calculate the fraction of the ultrasound intensity that is reflected at the muscle bone boundary. So let's just assume what is just leaving the surface of the muscle is still I, and what arrives here we can call it I1. What is leaving the boundary we can call it I2. of course, what arrives at the surface is called IR. They have called it IR. For easy understanding, we can do it like that. So we want at the boundary, in other words, we want I2 over I1. So we shall simply say I2 over I1 is the same as alpha, which has been given as Z1 minus Z2 over Z1 plus Z2, and this is squared. Because the powers of 10 are the same, I may not include the powers. So I'll simply say Z1. Z1 is maybe muscle, that is 1.7. Z2 is bone, I can say that is 6.4. Divide by 1.7 plus 6.4, and I will just square this. So the square is always positive, so it doesn't matter which one you subtract first, either bone minus muscle or muscle minus bone, the square is always positive. So when I press my calculator, so from my calculator I'm getting alpha as 0.34 to two significant figures. The intensity the intensity that is reflected at the muscle bone boundary is 0.34. That is the intensity reflected, the fraction actually. That is I2 over I1. Remember, I2 is what leaves the boundary and I1 is what arrives at the boundary. So the ratio of I2 over I1 is what we want, and that ratio is given by the intensity reflection coefficient, Z alpha. Okay, part 2. Calculate the fraction of the ultrasound intensity that is transmitted through a thickness of 3.4 centimeters. Calculate the fraction of the ultrasound intensity that is transmitted through a thickness. So we want the intensity transmitted through the muscle. Remember, intensity transmitted, now this will be I1, which has gone through the muscle, is going to be equal to what is incident on the muscle, that is I times e power negative mu x. So we want the fraction, that will be now I1 over I. That's the fraction we need, which will be equal to e negative mu times x. Okay, so the intensity transmitted, like we have seen, I1 is what I called it I1, the one which has been transmitted through the muscle, is equal to I, which is incident, e power negative mu x, and the fraction I1 over I is going to be e power negative mu. In the muscle, I think mu was given as 23 per meter. Then I will change x to meters. X thickness of the muscle is 3.4. So that is 3.4 times 10 power negative 2. So this is the value of E, the ratio. When we press our calculator, so from my calculator, I am getting 0.46. 0.46. So the ratio is 0.46. Use your answers in Roman 1 and Roman 2 to find IR over I. So you want to find the ratio of the intensity which is received back over the intensity which is entering the muscle. But I want you to note, we have already that intensity which has been transmitted, I1 is equal to 0.46 times I. That one is transmitted from the muscle to the boundary. And the intensity which is reflected at the boundary is given by the first expression, that is I2 over I1 is equal to 0.4. So it means I2 is equal to 0.34 times I1. Now, the ultrasound is being transmitted back from the boundary. It is leaving as I2 and it arrives here as IR. So you can find intensity transmitted back. So IR is what has been transmitted, but what is incident in the opposite direction is I2 times e power negative mu x. So it means IR is going to be, of course, this one is going to give us the same value as this one. So this part here is 0.46. So IR is going to be 0.46 again times I2. Then we do back substitution. We bring in I2 in this equation. So IR will be equal to 0.46 times 0.34 times I1. Again, back substitution, we bring in I1. So it means IR is going to be 0.46 times 0.34 times 0.46 times I. So it means the ratio IR over I as required is going to be simply 0.46 times 0.34 times 0.46. When I press my calculator, so from my calculator I get this as 0.072 as the ratio that is received back at the transducer or at the boundary. At the surface of the muscle. Okay. Explain the main principles behind the use of ultrasound to obtain diagnostic information about internal body structures. So this is a common question. Of course, here I gave it 6 marks. It could be more or less. So one, we must talk about how to produce ultrasound. Remember, it is the quasi-crystal across which a pin is applied so that the crystal vibrates to produce ultrasound. Number two, remember the transducer is placed on the skin which has been smeared with a gel so that there is no air between the transducer and the skin. Number three, remember the same transducer which emits ultrasound is the same transducer which receives. So it cannot do the two things at the same time. Therefore, short pulses are involved here. Number four, remember the reflected pulses are the ones converted into the voltage pulses by the same transducer to process an image. And we are interested in the intensity of the reflected ultrasound and the time it takes to go and come back. That is the time delay. Those concepts will help you to explain this fully and easily. So let us try to explain it fully and easily. First of all, we begin by producing ultrasound. So we shall say in the piezoelectric transducer, an alternating voltage is applied across the crystal. So in a piezoelectric transducer, an alternating voltage is applied across the quasi-crystal, which acts as the vibrating source. Which acts as the vibrating source of the ultrasound. So we have finished to produce ultrasound. In the piezoelectric transducer, an alternating voltage is applied across the quasi-crystal or across the let me just call it quasi-crystal, which acts as the vibrating source of the ultrasound. So the quasi-crystal, when we apply a PD across it, it vibrates to produce ultrasound. Now we have ultrasound. A transducer is going to be placed. So the transducer is placed on the skin smeared with smeared with a gel to exclude air. Exclude air between the transducer and the skin. Between the transducer and the skin. So the transducer is placed on the skin, smeared with a gel to exclude air between the transducer and the skin. Remember, the purpose of the gel is to act as an impedance matching substance. Then short pulses of ultrasound. Short pulses of ultrasound are sent into the body where they are partially transmitted and partially reflected. And partially reflected at boundaries between media. So inside the body, ultrasound can be partially transmitted, that is, it continues deeper, or partially reflected at the boundaries between different media. We are interested in the reflected pulse. So the reflected pulses are detected and converted into voltage pulses. By the same transducer. Into voltage pulses by the transducer, which are used to process an image. So the reflected pulses are detected and converted into voltage pulses by the transducer, which are used to process an image. Okay, which are used to process an image, of course, that is displayed. Let me just add that. An image which is displayed, or that is displayed. It is used to process an image that is displayed on the screen. What is very important is the intensity and the time delay. So we can say the intensity reflected gives information about the nature of the boundary. So the intensity reflected gives information about the nature of the boundary. And then the time delay, that is the time between transmission and reception, or time between transmission and receiving back the reflected pulse, will give information about the depth. So the time delay gives information about the depth of the boundary. So the time delay gives information about the depth of the boundary. The intensity reflected gives information about the nature of the boundary. So by doing that, you'll get those 6 marks because you have exhausted all that is needed. What is the most important points are 4. Applying a gel, short pulses, the intensity reflected, and the time delay. Those should appear in your essay, in your writing, or in your explanation. Okay, let's continue. State and explain one advantage of the use of high frequency ultrasound. One advantage of the use of high frequency ultrasound. What does high frequency mean? Of course, we know that frequency is inversely proportional to wavelength. So high frequency means short wavelength. And the shorter wavelength means there is less diffraction but more scattering around structures. If ultrasound scatters around structures, it means the small structures or smaller structures can be detected with high resolution. Therefore, high frequency means short wavelength. High frequency means short wavelength. High frequency means short wavelength, so smaller structures. So smaller structures can be resolved or can be detected. Smaller structures can be resolved or detected due to more scattering around them. So whenever the wavelength is shorter, it means there will be more scattering, and we are interested in ultrasound being reflected from from all parts around from all parts. So if there is more scattering around smaller structures, then they can easily be detected with a high resolution. The absorption or attenuation coefficient of ultrasound is given to be 24 per meter. A power beam of ultrasound is passed through a muscle of thickness 6.4 centimeters. Calculate the ratio. Intensity of the transmitted beam over intensity of the incident beam. So we have said for transmission, the intensity transmitted is equal to the incident intensity e power negative mu x. And we want the ratio I over I naught, which will be e power negative mu is 23, and x has been given as 6.4 times 10 power negative 2. So we simply press our calculator. So from my calculator, I have 0.23 as the ratio. You can also verify 0.23 as the ratio. An ultrasound transmitter emits a pulse. Remember we said ultrasound is sent in short pulses. Suggest why when the signal from the pulse is processed, any signal received later at the detector is usually amplified more. What does a signal received later imply to us? Of course, a signal which is received later means it went deeper and was reflected from a boundary which is deeper. Therefore, it will have a higher time delay. And since it has gone deeper, it has experienced a greater attenuation than the signal which is reflected earlier or which is received earlier. Therefore, the later signal has passed through a greater thickness. Later signal has passed through. Later signal has passed through a greater thickness. Greater thickness of the medium. So it has greater attenuation. So it has greater attenuation. So it has greater attenuation, or call it greater absorption. Or it has undergone greater attenuation, or it has undergone greater absorption. Or it has smaller intensity. So all that is meaning the same. So has smaller intensity. And if it has smaller intensity or has undergone greater attenuation, it needs more amplification. So that needs more amplification. Okay, so a signal which we receive later, it means it traveled a greater distance. So it has passed through a greater thickness. It has passed through a greater thickness of the medium. So it has greater attenuation, or it has undergone greater attenuation. Therefore, it has a smaller intensity. Thus, it will need more amplification. Okay. Explain the principles of the generation and detection of ultrasound. The other one was interested in producing images using an ultrasound scan. This one is interested in generation and detection. Generation and detection. So we have to be very careful here. So entirely this one, we are generating an ultrasound and detecting them. So remember, the same transducer which generates also detects the ultrasound. The same transducer which generates also detects ultrasound. To generate ultrasound, we must apply an alternating PD across the crystal. And the PD is going to make the crystal to vibrate. These vibrations of the crystal spread in the surrounding medium as ultrasound. When the vibrations or when the ultrasound again falls on the crystal, it again makes the crystal to vibrate. And these vibrations are converted into voltage pulses, which are picked and processed into an image. So that is, in brief, how the ultrasound is generated and detected. The same transducer producing is the same transducer detecting. Okay, so we can say in the center of the transducer is a piezoelectric crystal, such as quartz. The center of the piezoelectric transducer is a piezoelectric crystal such as quartz. The opposite sides of quartz are coated with silver. Are coated with silver to act as electrodes. So the opposite sides of the quartz are coated with silver to act as electrodes. So when the crystal is unstressed, the centers of the positive and negative ions in any one unit coincide. The centers of positive and negative ions in any one unit. Remember, quartz is made up of several repeating tetrahedral silicate units. So when the crystal is unstressed, the centers of the positive and negative ions in any one unit coincide. When a PD is applied, when an alternating PD is applied across the electrodes or across the crystal, when an alternating PD is applied across the electrode, an electric field is set up. An electric field is set up in the crystal. An electric field is set up in the crystal, which makes the centers of the positive and negative ions to move, which makes the centers of the positive and the negative ions to move and will no longer they will no longer be coincident. They will no longer be coincident. Of course, the positive ions move towards the negative electrode. So positive ions move towards the negative electrode. Negative ions. The negative ions move. The negative ions move towards. The negative ions move towards the positive electrode. So depending on the direction of the applied PD, depending on the direction depending on the direction of the electric field. Depending on the direction of the electric field created, the crystal will become slightly thinner, or the crystal will become slightly thinner or slightly thicker. In other words, it changes shape. The crystal will become slightly thinner or thicker. Will become slightly thinner or thicker. In other words, or that is to say, changes shape. So the crystal will become slightly thinner or thicker. In other words, it changes shape. Now, if the applied PD is in the ultrasound frequency range, the crystal will vibrate with the maximum amplitude. We say resonance occurs. So if the applied PD is in the ultrasound frequency range, that is of course above 20,000 hertz, the crystal resonates. Let's just say the crystal resonates. In other words, vibrates with the maximum amplitude. That's what I mean by resonates. These oscillations give rise to ultrasound waves in the medium surrounding the crystal. So these oscillations give rise to ultrasound in the medium surrounding the crystal. So these oscillations, because the crystal resonates, so these oscillations of the crystal give rise to ultrasound in the surrounding medium. Now that is production. If an ultrasound wave again falls on the crystal, if an ultrasound wave falls on the crystal or is incident on the crystal, quasi-crystal, it causes the crystal to vibrate, which again gives rise to alternating PD across the crystal. Which gives rise to an alternating PD across the crystal, which is processed into an image. So this last part is the detection part. If the ultrasound falls on the quasicrystal, again the ultrasound causes the crystal to vibrate. The vibrations are converted into, or the vibrations give rise. The vibrations give rise to an alternating PD across the crystal. This alternating PD is what is processed into an image by electronic circuits. So that is how ultrasound is generated and detected. In the center of the piezoelectric transducer is a quasicrystal whose opposite sides are coated with silver to act as electrodes. When unstressed, the centers of the positive and negative ions in any one unit coincide. When an alternating field is applied across the crystal, or across the electrodes, an electric field is set up in the crystal, which makes the centers of the positive and negative ions to move, and will no longer be coincident. The positive ions, of course, move towards the negative electrode. The negative ions move towards the positive electrode. So depending on the direction of the electric field which has been created, the crystal will either become slightly thinner or thicker. That is, the crystal changes shape. And if the applied PD is in the ultrasound frequency range, then the crystal is said to resonate. In other words, to vibrate with maximum amplitude. It is these vibrations or oscillations which give rise to ultrasound in the surrounding medium of the crystal. If again ultrasound wave is incident on the crystal, it causes the crystal to vibrate, which gives rise to alternating voltage or alternating PD across the crystal, which can be picked by electronic circuits, amplified, and processed into an image. So that is precisely how ultrasound is generated and detected. Okay, the specific acoustic impedance Z of some medium are given here. So we have air, gel, soft tissue, and bone. The density of a sample of bone is 1.7 times 10 power 3. Determine the wavelength in millimeters of ultrasound of frequency 9.0 times 10 power 5 Hertz. We want to determine wavelength. Of course, wavelength is going to be equal to the speed divided by f. Remember here, c is not speed of light. And we also know that the acoustic impedance Z is equal to the density times c. So it means c, the speed c is what we don't have. We have the frequency, we have z, so all we need is c. So when we put C here, when you combine these two equations, you notice that the wavelength will be equal to Z divided by density times frequency. Z will be equal to, wavelength will be equal to Z divided by density times frequency. When we substitute the value of Z for bone, Z is 7.0 times 10 power 6. The density is 1.7 times 10 power 3. The frequency is 9.0 times 10 power 5. So press our calculator. So our answer is turning out to be 4.6. Our answer turns out to be 4.6 millimeters, because to here it is giving me 4.6 times 10 power negative 3 in meters. So when I multiply by 1000, I get 4.6 millimeters. Okay. So the wavelength in millimeters is 4.6. Ultrasound of intensity I is incident normally on the boundary between two media of specific acoustic impedance Z1 and Z2 as shown in the figure below. So the intensity of the ultrasound reflected from the boundary is IR. The ratio IR over I is given by that expression. By making reference to the data for air, gel, and soft tissue, explain quantitatively why during medical diagnosis using ultrasound, a gel is usually put on the skin. We said normally the ultrasound transducer is placed on the skin, which has been smeared with a gel. Now the question is, you must use the data to explain quantitatively. Normally, when they say explain quantitatively, you should work out something, you should come up with a calculation. Okay, so we know for Z, air soft tissue boundary, those are the values, and the gel soft tissue, these are the values. So we are going to check the ratio for air soft tissue and then gel soft tissue, and we compare. So for air soft tissue boundary, I will begin with the air soft tissue. For air soft tissue boundary, the ratio IR over I is going to be equal to, so we substitute Z1, let's say air is Z1 and Z1 is 4.3 times 10 power 2. Then Z2, let's say it is soft tissue, 1.6 times 10 power 6, divide by 4.3 times 10 power 2 plus 1.6 times 10 power 6, and this should be squared. I press my calculator. So to one significant figure, this is approximately equal to 1. And what does this one mean? This means almost complete reflection. In other words, it means the intensity reflected is almost the incident intensity. So it's like all that is incident on the boundary is reflected back. So we are saying this means almost complete reflection, or no transmission. Almost complete reflection, almost no transmission. That's what it means. Let's check for gel soft tissue boundary. For gel soft tissue boundary, IR over I is going to be equal to, we substitute, the gel has a acoustic impedance of 1.5 minus the other one is 1.6 divided by 1.5 plus 1.6 and then squared. You notice that the difference is very small, so this is going to be equal to, so this is 1.04 times 10 power negative 3, and this is of course very close to 0. Very close to 0. So what does that mean? So we can simply say that there is very little reflection, there is more transmission. So we say gel enables almost complete transmission into the tissue. Into the tissue. Gel enables almost complete transmission into the tissue. Okay, so those are the 4 marks. They said explain quantitatively, so you must include all that. An ultrasound wave is incident on the boundary between two media. The acoustic impedances of the two media Z1 and Z2 as shown here. Explain the importance of the difference between Z1 and Z2. In other words, what is the importance of Z2 minus Z1 or Z1 minus Z2? Of course, we know that the intensity reflection coefficient alpha depends on that difference. So we say that the intensity reflection coefficient alpha is given by Z1 or Z2 minus Z1 over Z2 plus Z1, and this is squared. Therefore, it is depending on the difference. So if Z2 is very close to Z1, Z2 minus Z1 is very close to 0. So it means Z2 minus Z1 is approximately 0, is very small, approximately 0. Remember, this is intensity reflected at the boundary over intensity incident at the boundary. So if it is very small, it means there is more transmission than reflection. So this means mostly transmission occurs. In other words, more ultrasound is transmitted into the body, as we have seen with the previous example. And if Z2 is much greater than Z1, it means the difference Z2 minus Z1 is very large. And if that is true, it means the ratio is approximately equal to 1. The ratio will be approximately equal to 1. It means almost what is incident on the boundary is reflected. So we say mostly reflection. Mostly reflection occurs. So note very carefully that when Z2 is approximately equal to Z1, it means Z2 minus Z1 is approximately 0, and 0 over Z2 plus Z1 means alpha is approximately 0, which means more transmission, almost no reflection. And when Z2 is far, far greater than Z1, it means Z2 minus Z1 is approximately Z2. Z2 plus Z1 is still approximately Z2. So when you divide, you get approximately 1. And the ratio of 1 means more reflection occurs at the boundary. Okay. Ultrasound frequencies as high as 10 megahertz are used in medical diagnosis. State the advantage of the use of high frequency. We have seen why high frequencies are necessary. High frequency means better resolution at shorter wavelength. So there is a better resolution. There is a better resolution at shorter wavelength. Because high frequency means a shorter wavelength, there's a better resolution at shorter wavelength. And if there's a better resolution, it means smaller structures can be distinguished at high frequencies. So smaller structures can be distinguished at high frequency. Okay. Two media have acoustic impedances Z1 and Z2. Two media have acoustic impedances Z1 and Z2. The intensity reflection coefficient alpha for the boundary between the two media is given by that expression. Describe the effect on the transmission of ultrasound through the boundary where there is a large difference between the acoustic impedance. When there is a large difference between acoustic impedance, what does that mean? If this is a very large, if that is very large, in other words, Z1 is far, far smaller than Z2, the ratio here is going to be approximately equal to 1. If Z2 minus Z1 is very large, it means also that Z2 plus Z1 is approximately Z2. Z2 is very large, Z1 is very small. When you add or subtract, you get approximately Z2. And when you divide and square, you get approximately 1. So we are saying for Z2 minus Z1 very large, Z2 minus Z1 large, then alpha is approximately equal to 1. I've said if Z2 minus Z1 will be approximately equal to Z2 since Z2 is much bigger than Z1. And Z2 plus Z1 will also be approximately equal to Z2. So it means like you will be dividing Z2 over Z1, which is approximately 1. So for Z2 minus Z1 very large, alpha is approximately equal to 1. And this means almost, remember alpha is intensity reflected over intensity incident. So it means the reflected intensity will be nearly equal to the incident intensity. So transmitted intensity will be too small. So the reflected intensity would be nearly equal to the incident intensity. So the transmitted intensity would be too small. The reflected intensity would be nearly equal to the incident intensity. So the transmitted intensity would be too small. Okay. Data for the acoustic impedance Z and absorption coefficient mu for fat and for muscle are shown here. So they have given us Z values in SI units and they have given us linear absorption coefficients or linear attenuation coefficients in SI units. The thickness X of the layer of fat on an animal, as illustrated in the figure, is to be investigated using ultrasound. Okay. The intensity of the parallel ultrasound beam entering the surface of the layer of fat is I. So what is entering here is I. The beam is reflected from the boundary between fat and muscle. Let's say what arrives here is I1. Then what is reflected from the boundary is say I2. We shall say what is received back at the boundary at the surface is IR. The intensity of the reflected ultrasound detected at the surface of the fat is 0.012 I. The intensity of IR is actually, they're telling us IR is equal to 0.012 times I. The intensity of the reflected ultrasound detected at the surface is given by that. Part A, calculate the intensity reflection coefficient. Remember intensity reflection coefficient, that is alpha. Alpha is equal to the intensity which is reflected at the boundary over the intensity which is incident at the boundary. And this is given as Z2 minus Z1 over Z2 plus Z1, and this is squared. So we simply substitute. Yeah, they gave us fat as 1.3, mass was 1.7. So the powers of 10 are the same. I'll just substitute 1.7 minus 1.3 over 1.7 plus 1.3, and this should be squared. So I press my calculator. Okay. So this gives me 0.018 two significant figures. Then calculate the thickness x of the layer of fat. Calculate the thickness x of the layer of fat. Calculate the thickness x of the layer of fat. So they gave us the intensity received back as a fraction of the incident intensity as I. But we have I2 over I1 as this. So let's first find I1. So intensity transmitted for the first time is going to be I e power negative mu x. And this is going to be equal to, because they gave us mu as, mu is 20 what? Mu through fat is 48. So this will be, okay, I will just record that as the first case. Then intensity, which is reflected, I2 is equal to 0.018 times I1. Then the intensity which has been transmitted through in the opposite direction is going to be actually I1 which is leaving I2 which is leaving the boundary backwards times e power negative mu times x. So we now do what we call back substitution. We do back substitution. Remember IR has been given as 0.012I. So I'm just going to do back substitution. So where there is IR, I will put there 0.018 of 0.012I. I2 is 0.018. Where there is I1, I put I1, which is times I e power negative mu x. Remember here there was I2 times, it was I2 times that. So I will just multiply by e power negative mu x again. So I has cancelled. So I now have that 0.012 is equal to 0.018 e power negative 2 mu x. Okay. So introduce natural logarithm. When you introduce natural logarithm, ln of 0.012 over 0.018 is going to be equal to negative 2 times 48, that is mu, times x. So when you press your calculator to find x, pressing my calculator, so x is 4.2 times 10 power negative 3 in meters. And they want the answer in centimeters, so I multiply by 100, it will be 0.42 in centimeters. Data for some media are given in the figure below. Use data, so they have given us speed of ultrasound in air, gel, soft tissue, and bone. They have given us acoustic impedance. Use data from the figure to calculate a value for the density of bone. So density of bone, so rho, density is equal to Z over C. So Z for bone, Z is 7.0 times 10 power 6, and the speed is 4,100. So this is giving me 1,700 from my calculator. 1,700. A parallel beam of ultrasound has intensity I. It is incident at right angles to a boundary between two media as shown in the figure here. Okay, it is incident at right angles to a boundary between two media. The media have acoustic impedances Z1 and Z2. The transmitted intensity of the ultrasound beam is IT, and the reflected intensity is IR. State the relation between IT, and IR, of course, by conservation of energy. I is incident, part of it is reflected, that is IR, and part of it is transmitted. So it is just IR plus IT by conservation of energy. The reflection coefficient alpha is given by that expression. Use data from the figure 10.1, that is the table, to determine the reflection coefficient alpha for the boundary between gel and soft tissue. Boundary between gel and soft tissue. Notice that for gel, this is the speed. Soft tissue is that. Acoustic impedances for gel and soft tissue 1.5 and 1.6. So we want alpha. So for gel and soft tissue, alpha is going to be, since they gave us the formula Z1, I'll simply say soft tissue is 1.6, gel is 1.5 over 1.6 plus 1.5, and this is squared. I ignore the powers of 6 because they are the same. So this is giving me 1.04 times 10 power negative 3, or approximately 0.0010. That is for alpha. Then air and soft tissue. Alpha is going to be, for soft tissue is 1.6 times 10 power 6. And for air, I think they gave us 4.3 times 10 power 2. Divide by 1.6 times 10 power 6 plus 4.3 times 10 power 2, and this should be squared. I press my calculator. So from my calculator, this is giving me 0.9989, which is approximately 1.0. Okay. By reference to your answers in B Roman 2, explain the use of a gel on the surface of skin during ultrasound diagnosis. We have seen when there is gel, we have seen that what is reflected is very small. There is more transmission. But we see when there is no gel, it is air, soft tissue, it is like almost all that is incident on the skin is reflected back. So we say that there is little transmission. There is little transmission. There is little transmission at the air, skin boundary. There will be little transmission at the air skin boundary. There is little, let me just say very little. There's very little transmission at the air skin boundary, and almost complete transmission, almost complete transmission at a gel skin boundary. At a gel skin boundary, when ultrasound when ultrasound wave when an ultrasound wave travels in or out of the body. There is very little transmission at the air skin boundary and almost complete transmission at the gel skin boundary when an ultrasound wave travels in or out of the body. So therefore it means we need a gel. For no gel, majority reflection occurs at the surface. With gel, little reflection occurs when a wave travels in or out of the body. For no gel, there's majority it is reflection at the surface. With a gel, there is little reflection on the surface when a wave travels in or out of the body. Okay, so we need a gel. Explain why acoustic impedance is important when considering reflection of ultrasound. Of course, we are always finding the reflection coefficient of reflection or intensity reflection coefficient from the difference in the acoustic impedances. So we are going to simply say the difference in acoustic impedance determines the fraction of the incident intensity that is reflected at the boundary. The difference in acoustic impedance determines the fraction of incident intensity that is reflected at the boundary. Okay. Data for the acoustic impedance and absorption or attenuation coefficients of muscle and bone are given in the table. The intensity reflection coefficient is given by that expression. So they have given us acoustic impedances and the values of mu or the attenuation coefficients. The attenuation of ultrasound in muscle follows a similar relation to the attenuation of X-ray in matter. That is, I transmitted is going to be I naught e power negative mu x. That's what it means. A parallel beam of ultrasound of intensity I enters the surface. So this will be intensity. I call that one I1 and I'll call this one I because the incident is I. A parallel beam of ultrasound of intensity I enters the surface of a layer of muscle of thickness 4.1 as shown here. So calculate the intensity reflection coefficient at the muscle bone boundary. So they have told us what is leaving here is I. Let's say what arrives at the boundary is I1. Maybe what is reflected is I2 and what is received back is IR. So we want to calculate the intensity reflection coefficient at calculate the intensity reflection coefficient at the muscle bone boundary. So we want to find alpha. Alpha is equal to Z2 minus Z1 over Z2 plus Z1, and this should be squared. So they gave us the values of Z in the table, 1.7 and 6.3. So this would be 6.3 minus 1.7 over 6.3 plus 1.7, and this should be squared. I ignore the powers of 10 because they are the same. So from my calculator, I have this as 0.33. Then the fraction of the incident intensity that is transmitted from the surface of the muscle to the surface of the bone. So in other words, we want I1 divided by I. I1 over I. So that is I1 is equal to I e power negative mu x. So the fraction is I1 over I, which is e power negative. They gave us mu for muscle has been given as 23, and the thickness is 4.1 centimeters, so it will be 4.1 times 10 power negative 2. So we press the calculator. Remember, this is a negative. There's a negative here. So from my calculator, I'm getting the ratio as 0.39 to two significant figures. Then the intensity, actually the intensity in terms of I that is received back at the surface of the muscle. We want the intensity received back. So the intensity received back will be IR, but remember it leaves as I2 from the boundary, times e power negative mu x. And remember from the first equation, this one here, the intensity reflection coefficient, this is I2 over I1. Intensity reflected from the boundary of the intensity incident. So this is going to be I2, which is I2 over I1 is 0.33. So this will be 0.33 times I1 e power negative mu x. But again, remember, I1 is equal to 0.39 times I. So it means this is going to be 0.33 times I1, which is 0.39 times I, then e power negative mu x. Remember, we are now again going to substitute for mu and x in the opposite direction. So mu was 23 and x was 4.1. So we get the same thing as 0.39. So this is going to be 0.33 times 0.39 times 0.39 again times I. So that is IR. So the ratio or the intensity that we will have received is going to be 0.33 times 0.39 times 0.39. So this gives me 0.050 as the ratio. Okay. Ultrasound may be used to obtain information about internal body structures. Suggest why the ultrasound from the transducer is pulsed. What is the purpose of pulsing? Why pulsed? Remember, the same transducer which emits ultrasound will detect it. And it emits by vibrating, and it detects, when it detects, it has to vibrate. So it can't vibrate for emitting and at the same time vibrate for reflection at the same time. So we simply say the same transducer transmits, the same transducer emits and detects. ultrasound. So it cannot detect and emit at the same time. It cannot detect and emit at the same time. So pulses are going to allow ultrasound to be detected in between the emitted and or in between transmitted pulses. So pulses allow the reflected signal to be detected between emitted pulses So pulses allow the reflected signal to be detected between emitted pulses so as to determine the nature or the depth and nature of boundaries. To determine the nature and the depth. So to determine the depth, let me begin with the depth. To determine the depth and the nature of boundaries. Okay, so that is why ultrasound is pulsed. State what is meant by specific acoustic impedance. Specific acoustic impedance. Of course, we started with such a question, the product of the ultrasound or the speed of ultrasound in a medium and the density of the medium. Product of the density of the medium, product of the density of the medium product of the density of the medium and the speed of ultrasound in the medium. So that is the acoustic impedance. A parallel beam of ultrasound of intensity I naught is incident normally on the boundary between two media as shown here. They have showed us the media here, and there is a boundary. The media have specific acoustic impedances Z1 and Z2. The intensity of the ultrasound beam transmitted across the boundary is IT. Explain the significance of the magnitudes of Z1 and Z2. Of course, we have already seen the significance. If they are exactly the same, the difference is approximately zero. It means there is almost no reflection. If they are far greater than each other, the difference is infinitely large. It means even the sum is infinitely large. There is almost no reflection but total transmission. So we are saying that if Z1 is approximately the same as Z2, 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 then it means when you subtract, you are most likely going to get 0. So we say I2, or okay, intensity transmitted IT over I naught is going to be approximately 0. Reason, intensity reflected over the incident intensity is approximately 1. No, it's approximately 0. Intensity reflected over incident intensity is approximately 0. When they are approximately the same, then that means the intensity transmitted is approximately 1, not 0. Reflected is approximately 1, transmitted is reflected is approximately 0, transmitted will be approximately 1. So there is almost no reflection, but there is more transmission. So we say mostly transmission occurs, very little reflection. Okay, and if Z2 or if Z2 is much greater than Z1, if Z2 is much greater than Z1, remember we are substituting the formula alpha is equal to Z2 minus Z1 over Z2 plus Z1, and this is squared. If Z2 is many times bigger than Z1, it means when you subtract, you get almost Z2. When you add, you get almost Z2. When you divide, you get 1 for reflection. For transmission, then it will be 0. Because remember, by conservation of energy, when you add the ratios of reflection and the ratio of transmission, you should get 1. So this means I transmitted over incident intensity is approximately 0 because reflection is approximately 1. So we say mostly reflection occurs and little transmission. And very little transmission. Okay, so that is the significance of Z1 and Z2 values. A parallel beam of ultrasound has intensity I naught as it enters a mass of thickness 4.6 centimeters, as illustrated in the figure here. The intensity of the beam just before it leaves the muscle is IT. The ratio I naught over IT is found to be 2.9. I naught over IT is found to be 2.9. Calculate the linear attenuation coefficient. Calculate the linear attenuation coefficient, mu, of the ultrasound in the layer of the muscle. So intensity transmitted, that is IT, is supposed to be equal to I naught times e power negative mu x. But they have given us I naught over IT as being that. I naught over IT is this, so I naught is going to be 2.9 times IT. I naught is 2.9 times IT, so I'll just substitute here. So IT is going to be equal to, because I naught is 2.9 times IT, I'll just put here 2.9 times IT e power negative. We don't know mu, but x is, since we want mu per centimeter, I will not convert x. So x is going to be 4.6 centimeters. So we introduce natural logarithm. So you will notice that actually ln of 1 over 2.9 is going to be equal to negative mu times 4.6. So I press my calculator. So when you divide to get mu, you get mu as 0.231, 0.231, or approximately 0.23 per centimeter. State what is meant by the specific acoustic impedance of a medium. So we have seen this is the product of the density of the medium and the speed of ultrasound in the medium. The product of the density of the medium and the speed of ultrasound in the medium. The intensity reflection coefficient alpha is given by that expression. Explain the meanings of the symbols in this expression. Alpha. Of course, alpha is the ratio of the reflected intensity to the incident intensity. Alpha is the ratio of reflected intensity to the incident intensity of ultrasound. Then Z2 and Z1, of course, these are specific acoustic impedances of the media on each side of the boundary. The specific acoustic impedance specific acoustic impedances of the media on each side of the boundary. Specific acoustic impedances of the media on each side of the boundary. A parallel beam of ultrasound has intensity I naught as it enters a muscle. The beam passes through the thickness of 3.4 centimeters of muscle before being incident on the boundary with the bone as shown here. Okay, so what is leaving here is I naught. And we can think of what is reaching here. Let's think of what is reaching here to be I'll call it IM. What is reaching there is IM. I can think of what is reflected at the boundary as being okay, let me call it IR. The intensity of the ultrasound beam as it enters into the bone is IT. As it enters into the bone, it is IT. Some data for muscle and bone are given in the table here. So they have given us Z values and values of mu. Calculate the ratio IT over I naught. That is the ratio of the incident of the intensity transmitted through the bone over the intensity which is incident on the surface of muscle. So when it goes through the muscle, what is transmitted through the muscle, I call it Im. And using Im, which is transmitted through the muscle, is equal to I naught e power negative mu x. And this will be equal to I naught e power negative mu, because it's going through muscle, that will be negative 23 times the thickness of muscle, which is 3.4, times 10 power negative 2. So it means intensity which is transmitted through muscle in one direction is going to be 0.4567 I naught from my calculator here. Then we can look at the boundary to see what is reflected, and then we can see what is transmitted. So at the boundary, alpha is the intensity reflection coefficient. Remember, alpha is going to be equal to intensity reflected at the boundary over the intensity incident at the boundary. And this will be equal to, remember they have given us the formula for Z. So Z2 will be bone boundary 6.3, then muscle 1.7 over 6.3 plus 1.7. And this should be squared. I press my calculator. So this is giving me 0.33, and this means okay, 0.33. That is the fraction which has been reflected at the boundary. Remember, the fraction which is transmitted at the boundary, I will call it IT, that is transmitted through the boundary, over what is incident on the boundary is Im. Of course, this is going to be 1 minus alpha, which is going to be 1 minus 0.33. That is the fraction which is transmitted through the boundary, IT. So IT is 1 minus 0.33, which is 0.67. That is IT. So all we need is to express it in terms of I naught. So IT is going to be 0.67 times Im. We remove Im. We have Im is equal to 0.475 I naught. So this will be 0.67 times 0.457 I naught. Press my calculator. So from my calculator, this is 0.31. So the ratio required to give us these 5 marks is simply 0.31. This question was looking for the ratio which is transmitted, the fraction, the intensity which has been transmitted, and the ratio, of course, that is IT over I naught, which is 0.31. Okay. A parallel beam of ultrasound is incident normally on the surface of a layer of fat of thickness 1.1 centimeters as shown in the figure. For the ultrasound, I1 has been defined, I2 defined, I3 defined, and I4 defined. They even gave us some data in the table. Okay, they gave us the density. This is for fat. They gave us Z for fat, density for fat, and coefficient mu for fat. Know that it's first of all going through, it is actually in fat. Okay. Part A, calculate the time interval between a short pulse of ultrasound initially entering the layer of fat and then returning. So if it is returning, it is traveling the distance twice. It is traveling the distance twice. So the time is going to be equal to the speed, no, the distance over the speed. Time will be the distance divided by the speed, and the speed is going to be got from Z over density. Speed is the Z over density. They gave us Z for fat as 1.4 times 10 power 6, and they gave us the density as 940 in the above table. You can check. So that is the speed. But remember, the distance is twice. So the time is going to be 2 times the distance in one direction, which is 1.1, times 10 power negative 2 to change it to meters, then divide by the speed. So in the numerator, we shall have 1.4 times 10 power 6. Then the denominator, you have 1.4 times 10 power 6. And 940 goes up because you are dividing by the speed. So I press the calculator. Remember how I multiplied by 2 because it is initially entering and returning back. So this is giving me time as 1.50, 1.5 times 10 power times 10 power negative 5. Then the ratio, calculate the ratio I2 over I1. Calculate the ratio I2 over I1. I2 over I1. I2 is what has been transmitted towards the boundary, and I1 is what was incident onto the fat. So I2 is equal to I1 e power negative mu x. So the ratio I2 over I1 is going to be e power negative mu, and mu for fat has been given in the table as 48 times the thickness 1.1 times 10 power negative 2 in meters. So I press my calculator. So this gives me 0.59. 0.59. Intensity I4 is 0.33% of the intensity I1. In other words, I4 is 0.0033 times I1. You divide by 100. 0.33 0.33 divided by 100. Determine the ratio I3 over I2. So we go back and see what is I3 over I2. But we have here I2. We have I2 is equal to 0.59 I1. Don't forget that I2 is 0.59 times I1 from this part here. This part here I2 over I1 is 0.59. So it means I2 is 0.59 times I1. Okay. Then I3, remember, it is at the boundary. I3 is at the boundary. I3 is at the boundary. And we don't have the coefficient, the acoustic impedances across the boundary. We only have for fat, so we don't need to use that. I4 is also transmitted through the fat in the opposite direction. So I4 is equal to I3 because I3 is what leaves the boundary. I4 is incident on the surface in one, it has been transmitted this side, but what leaves the other side is I3. So we use the formula for transmission, that I4 is equal to I3 e power negative mu times x. So mu is the same, 48, and x is 1.1 times 10 power negative 2. So it means I4 is also I3 times, we had got this as 0.59. 0.59. Now we just do back substitution. So remember I4 is 0.003. So where there is I4, I'm putting there 0.0033 I1. This is equal to I3, which is this, the other side is I3, that is 0.59 times I3. So I must remove I1 here. Note that I1 from this equation is I2 over 0.59. So this will be 0.033 times I2 over 0.59 should be equal to 0.59 times I3. So I want to make I3 the subject over I2. So this will simply be 0.033 divided by 0.59 times 0.59 in the denominator. So when I press my calculator, so this is giving me 9.5 times 10 power negative 3. Okay. The specific acoustic impedance of the muscle is greater than that of the fat. In other words, Z2 is greater than Z1. State the effect, if any, on the value of the ratio I3 over I2 of an increase in the difference between the acoustic impedances. Now that this is the fraction which is reflected at boundary, if there is an increase in the difference, that fraction increases. So in other words, because there is more reflection, so the fraction increases. So I3 over I2 increases. There is more reflection. There is more reflection and a little transmission. There is more reflection and little transmission. Okay. Explain why ultrasound used in medical diagnosis is emitted in pulses. Right now we now know why pulses. So the same transducer emits and it takes ultrasound. It can't do this at the same time. The same transducer emits and detects ultrasound. So it cannot emit and detect at the same time. It cannot emit and detect at the same time. It cannot emit and detect at the same time. Hence, pulses allow detection to occur in the time between emitted pulses. The time between emitted pulses, you can even add more if you want, since it allows the reflected The reflected signal to be distinguished from the emitted signal. So that is the purpose of short pulses. Okay. Explain the principles of the detection. We only want detection of ultrasound waves used in medical diagnosis. Detection. So we know that at the center of the piezoelectric transducer is the quasi-crystal. So the piezoelectric transducer is the quasi-crystal. Ultrasound incident on the quasi-crystal makes it vibrate. The vibrations produce alternating PD across the crystal, which can be processed by electronic circuits into an image. So the piezoelectric transducer is the quasi. Ultrasound incident on the crystal makes it to vibrate. Makes it to vibrate. The vibrations produce alternating PD across the crystal. The vibrations produce alternating PD across the crystal, which can be processed, by electronic circuits into an image. So that is how we detect. It is the same transducer. The quasi-crystal is the same transducer which detects. When ultrasound falls on the crystal vibrates and produces an alternating PD across it. The alternating PD is the one which is processed by electronic circuits into an image. Okay. The specific acoustic impedance Z of some media are given here. They have given us air, gel, and soft tissue. The acoustic impedances of the two media are Z1 and Z2. The intensity reflection coefficient alpha is given by that. Calculate to three significant figures the fraction of the ultrasound intensity that is reflected at the boundary. So we just substitute alpha is equal to 1.6, that is between air and soft tissue. 1.6 times 10 power 6 minus 4.3 times 10 power 2 divided by 1.6 times 10 power 6 plus 4.3 times 10 power 2, and this is squared. So when I press my calculator, so from my calculator this is 0.999 to three significant figures as required. Use your value in B Roman 1 to explain why gel is applied to the surface of the skin during ultrasound scan. Why is gel added? So the specific acoustic impedances, or the Z values for gel and skin, are more similar. They are almost the same. So Z values of gel and skin, when you look at them, the Z values of gel and skin are more similar. Or they are almost the same. So it means alpha reduces. So alpha reduces. In other words, the intensity reflection coefficient becomes smaller. Alpha reduces. And when alpha reduces, when the fraction intensity reflection coefficient is smaller, it means more ultrasound is transmitted, meaning more ultrasound is transmitted than reflected. So it means because the Z values are almost the same when you look at them, Z for gel is 1.5, Z for soft tissue is 1.6, so they are almost the same. So because the Z values of gel and skin are more similar or almost the same, it means alpha becomes smaller. Intensity reflection coefficient becomes smaller since the difference is very small. A small difference in Z values implies more transmission than reflection. Without the gel, without the gel, without the gel, most of the ultrasound without the gel, most of the ultrasound is reflected just on the skin surface. Just on the skin surface, making the scan not possible. So that makes the scan not possible. Yeah, I think we have at least tried to answer some questions, and I want episode one to stop at that point. So we shall start with episode 2 next time. So thank you.